Hi, my name is Kit Yates. I'm a senior lecturer in mathematical biology at the University of Bath, and it is my pleasure to be giving this Gresham lecture this evening on the maths of life and death. So I'm going to break the talk down into three main parts. First part is going to be looking at the places where mathematics has had an impact in the medical arena and places where a bit of a better knowledge of mathematics can really help us out. Secondly, I'm going to look at places where maths appears in the newspaper headlines or on TV or on the radio, so maths in the media. And thirdly, I'm going to look at maths in the criminal justice system. I'm going to try and understand places where maths can crop up in the context of crime. So firstly, to talk about medicine, I'm going to start off with a little problem which you can have a go at home if you'd like to, and it's going to be a problem about screening. So I'm going to talk to you about screening programs in the United Kingdom specifically, and I'm going to talk specifically about breast cancer, although this is similar for other areas. So I'm going to give you some statistics. Here's one of them, which is about the probability that a woman over 50 who regularly gets invited to the screening program in the UK, so we invite women between 50 and about 72 or 73 for regular screens every 3 years, the prevalence of breast cancer is as low as 0.4%. So that means that of 1,000 women randomly selected in the population over the age of 50, 4 of them will have undiagnosed breast cancer. Another statistic that I'm going to give you is about the screening test itself. So if a woman has breast cancer, the probability that she tests positive is 90%. So 9 times out of 10, if you have breast cancer and you go for a screen, you will be told to come for follow-up tests. 1 time out of 10, unfortunately, your breast cancer will be missed. Another statistic is about the number of times that women who don't have breast cancer will get the correct result. So actually, a woman that doesn't have breast cancer goes for a screen. The probability that she incorrectly tests positive, so gets a false positive, is 10%. But again, 9 times out of 10, she will be correctly told that she doesn't have breast cancer. So here are 3 statistics about the background prevalence of the disease in the population, which is quite low, and the probability that if a woman has breast cancer that she tests positive, and if she doesn't, also the probability that she tests positive. And I'm going to ask you a question that was asked to a number of German doctors a few years ago, and this is the question, and we'll see if you can do any better than they did. So which of the following best characterizes the probability that a patient with a positive mammogram actually has breast cancer? So which of the following best characterizes the probability? So I'm going to give you some numbers, which will be, I'll put them down as percentages. They're going to characterize probabilities that a patient with a positive mammogram, so someone who gets sent a letter saying you need to come for further follow-up tests, actually has the disease. So I'm going to show you 5 numbers and you can choose between them. So is it A, 90%? Is it B, 81.0%? Is it C, 49.1%? Is it D, 3.5%? Or is it E, 0.4%? So just to recap, the probability that a woman over 50 has breast cancer, undiagnosed breast cancer in the UK, is about 0.4%. If a woman has breast cancer, she goes for a screen, then the probability that she tests positive is 90%. So 9 times out of 10, she gets the correct result. 1 time out of 10, that breast cancer is missed. If a woman doesn't have breast cancer, the probability that she incorrectly tests positive is 10%. So again, 9 times out of 10, she'll be correctly told she doesn't have breast cancer, and 1 time out of 10, she'll be given the incorrect false positive diagnosis. So what's the probability that if someone gets a positive mammogram that they actually have breast cancer? So I'll give you a second to think about this. If you're watching this afterwards, then you can just pause the video, but I'll just pause for 10 seconds to allow people to think. Okay, so the correct answer, and I think this is a surprise to many people when they first see this problem, it was certainly a surprise to me when I hadn't thought about this rigorously mathematically, is D. It's just 3.5%. So that seems really alarming. Is it possibly true that of all the letters that get sent out, only 3.5% of them, are actually correct positive diagnoses? Where does this figure come from? Well, I'll tell you, before we go into the detailed maths, I'll tell you that of these German doctors, I think they were actually all gynecologists, fewer than 20% of them got the answer to this question right, which suggests that actually they would have been doing better purely guessing at random in this question. So it is a difficult problem, and if you got it wrong, there's absolutely no shame in that. I didn't give you much time to work it out mathematically, but let's think about how we can actually get a handle on this figure. So rather than playing around with percentages and decimals, I want to think about 10,000 representative women who get tested in this over 50 population. So of those 10,000 women, I've said that 0.4% of them will have breast cancer, undiagnosed breast cancer. So that's 40 cases in this 10,000 population. The remainder, the vast majority, 99.6%, so that's 9,960 of these 10,000 women, so almost all of them, will not have breast cancer. But all of them still get asked to go for a screen. So they all get tested and they get a positive or negative result back. So of the women that have breast cancer, 90% of them will be correctly identified as having breast cancer. So that's 36 true positive results. So 90% of 40 is 36. Unfortunately, 10% will be given a false negative diagnosis. So that's 4 women given a false negative diagnosis. Of the women that don't have breast cancer, again, the vast majority will be correctly told they don't have breast cancer. So that's 90%, that's 8,964 true negative results. But because the size of this second population is so large, even a 10% false positive rate, 10% of 9,960 is 996. That's a huge number. That's nearly 1,000 false positives. And you can see that that massively outweighs the number of true positive diagnoses. So actually, the number of true positives is massively dwarfed by the number of false positives. So if I work out the number of true positives as a proportion of the total number of positives, the proportion of correct positives is just 36 divided by 36 plus 996, the total number of positive results, the total number of letters that get sent out saying, please come for follow-up investigation. And when you work that out, it turns out to be just 0.035 or 3.5%. So it can be incredibly low. So what's the problem with this? Well, there are a number of problems, and I have a book called The Maths of Life and Death, the same title as this talk. And in this book, I tell the story of Kaz Daniels, who's a mother of 3 from Northampton. Kaz Daniels gets invited for her first ever screen, and a few weeks later, she gets sent a letter on a Thursday afternoon saying, you need to come for further follow-up tests next Monday, so 3 days' time. And she thinks because of the urgency of the follow-up and because it says, you've been invited to come for further tests, she assumes quite naturally that she has breast cancer, and she makes plans about what's going to happen to her kids when she dies. She doesn't eat properly over the weekend. She doesn't sleep properly. She suffers severe psychological stress because of this letter. And actually, when she goes to the follow-up screen, the follow-up test on the Monday, it turns out that she didn't have breast cancer, which was always likely to be the case because we know that the vast majority of these positive letters or these requests for follow-up investigation are false positives. So I think it's important that people understand that there is a high rate of false positives when we have a disease which has a low prevalence in the population and we are screening lots of people for it. But that's not the only problem. So this is a quote from Muir Gray, who's the former director of the UK National Screening Programme. He said, all screening programmes do harm. Some do good as well, and of these, some do more good than harm at reasonable cost. But he says all screening programmes do harm. Well, what does he mean by this? Well, there is another problem that lots of small, potentially benign tumours will be picked up with these screens. Tumours which will be so small or slow growing that they would never cause a problem in that woman's lifetime. Nevertheless, when someone hears the word tumour or cancer, something goes off, some alarm goes off in their brain, and they think, I have to do everything that I can to avoid this existential threat. And so people often end up undergoing unnecessary surgery, which carries with it its own risks. So with radiotherapy, for example, there's an increased, for breast cancer, there's an increased risk of heart disease, for example. So they end up undergoing these dramatic, sometimes life-changing surgeries, sometimes full mastectomies, which can be incredibly psychologically difficult to deal with, as well as physically, undergoing general anaesthetic, which brings with it its own risks, when actually the tumour that was picked up by the screen maybe didn't have any potential to cause them damage over the course of their natural lifetime. And the other problem with all these false positives is that these follow-up tests are sometimes much more invasive than the screens. Screens, I gather, I've never been for one myself, but I gather they are particularly uncomfortable, but potentially follow-up tests involve things like biopsies, which are non-trivial operations to undergo, particularly for things which turn out to be false positives. So screening programs are not without their problems. Now, the other lesson that I want us to learn about screening programs is that we should start to expect these false positives. So what do I mean by that? Well, if you go for consecutive tests with a false positive rate of 10%, let's assume that you get false positives independently on each test. That may or may not be the case with mammograms. There may be a particular reason why you're flagged up as being a false positive or not. But let's assume that these tests are independent of each other each time you go. If each time there's a false positive rate of 10%, as there is with mammograms, how many tests you need to go to before it becomes more likely than not that you're going to have received a false positive test result. So we can work this out for a number of tests using a bit of fairly straightforward mathematics. So what I'm going to do is I'm going to say for each number of tests that you undergo, firstly, what's the probability of not receiving a false positive, because that's actually easier to work out. And then what's the probability of receiving a false positive. So for one test, the probability of not receiving a false positive, well, that's just 0.9. Okay, so if the probability of receiving a false positive is 10% or 0.1, the probability of not receiving one is 0.9. So I'll write that in a slightly circuitous way as 0.9 to the power of 1, which is just 0.9. So the probability of a false positive is 10% or 0.1. That's just the false positive rate that we were given for a single test. So it seems a bit trivial for a single test, like I've gone a bit too far in trying to work this out, but it becomes more easy. It makes it easier when I'm thinking about more tests than one. So when I've gone for my second test, in order to have had no false positives so far on both of these tests, I need to have had no false positive on the first test. That happens with probability 0.9. And no false positive on the second test, and that happens independently with probability 0.9. So I have to multiply 0.9 by itself to find out the probability of no false positive being 0.81, and therefore the probability of there being a false positive, or at least one false positive in those two tests, being 1 minus that at 0.19. So that's after 2 tests. After 3 tests, then I need to have no false positive on the first, and on the second, and on the third. So that's 0.9 to the 3, which is 0.729. That's the probability of having no false positive. And so the probability of having at least one false positive during that time is 1 minus that, which is 0.271. So it's getting higher, you can see. And actually, I'm not going to go through all the calculations, but by the time you get to 7 consecutive tests, the probability of no false positives in any of those is 0.9 to the 7, which is 0.478, which is just below a half. So the probability of at least one false positive during that time is 0.522, which is just above a half. So after you've been for 7 independent screens or tests with a false positive rate of 10% in each one of them, independent of the others, the probability of receiving at least one false positive outweighs the probability of not receiving a false positive. In short, it becomes more likely for you to have received a false positive than for you not to have received a false positive. And so it's worth bearing this in mind, that if you go for enough screens, then you should start to expect these false positives. For women undergoing screening for breast cancer, for example, if you get invited for screening from the age of 50 every 3 years until you're 72 or 73, then you might expect to have 7 or maybe even 8 of these screens over the course of that time period. So you might expect to receive false positive results. So the take-home messages from this part of the talk are: take screening results with a pinch of salt. What I am absolutely not saying is don't go for screening. Please do continue to go for screening. Screening programs do catch cancers early, and it does mean that you can have much better treatment outcomes if you catch cancer early. But what I am saying is that you should, if you get a letter telling you need to come back for further tests, of course you should go for those further tests, but you shouldn't freak out about it. You should bear in mind that false positives are surprisingly likely in these screening tests where we have a low prevalence in the population, so a small number of people have this undiagnosed disease, and the tests that we're using for them lack what's called specificity. So they give a non-trivial rate of false positives. And this isn't just for breast cancer screens, this also goes for things like prostate cancer screens as well. So anywhere where the prevalence is low and we're using a test which lacks a little bit of specificity, it has some non-trivial rate of false positives, you need to take your initial screening result with a pinch of salt and go for follow-ups and get it checked out. And you should also start to expect these false positives as well. The way that I like to think about screening results is when a company is hiring for a job. They send out an advert, and the idea is that they get people to send in their CVs, and they can sift through those CVs fairly quickly and easily. And that's like a screening program. We send everyone who's at slightly higher risk of getting this disease, we send them a letter saying, come for a test. We'll do a cheap, easy to use test, like a mammograph, for example, and it won't be the most accurate test, but we can quickly try and find out the people who are going to need follow-up tests. So just like with the job interview, you sift through these CVs and you say, right, I'll take these candidates. This is a broad brush measure, but what I want to do is throw them, the more expensive stuff like the interview, which is intensive in terms of the people it takes up, or the assessment center. I'm going to get this person to come now. We're going to use some more accurate tests to find out whether this person gets the job. And that's exactly the same with the screening program. You get a letter saying, come for some more accurate tests so I can diagnose whether you actually have this disease or not. And the whole point of that is, the whole point of the analogy rather, is that just because you get asked for an interview for a job, you shouldn't assume you've got the job. In exactly the same way, just because you've been invited for follow-up tests from a screen, you shouldn't assume you have the disease that is being screened for. And that's how I would view the results of screening. And the other thing is to ask for a second opinion. So the example at the start shows you that the doctors who are often handling the statistics, who are handling our diagnoses, are not always the best equipped statistically to understand the mathematics underlying these diseases. And so I think asking for a second opinion, not just from a different doctor, but also asking for a second test. If you get a second test, even if it's no more accurate than the first test, that can dramatically reduce the rate of false positives. So 2 tests really can be better than 1. So I'm going to segue into this second part of the talk, which is about the places where maths can come up in the media, in newspaper headlines, in TV or on the radio. But I'm going to continue to talk about medical applications. So it seems that almost every day there's a newspaper headline or story that comes up about the impact of one of our lifestyle choices on something to do with our health. So it might be that we are eating too much of the wrong thing, or we're not eating enough of the right thing, or maybe we're sleeping too long, or we're drinking too much, or we're not drinking enough maybe. So there's lots of headlines about our lifestyle choices, and the reason they're often in the headlines is because people genuinely want to try to make the best lifestyle choices that they can in order to improve their health and to improve their well-being. And it's completely reasonable that people want to do that, but we need to be careful about the way these stories are presented to us. So I'm going to tell you a cautionary tale. So back in 2009, the World Cancer Research Fund published a paper, which was a review paper which looked at the results of over 100 other papers. It was a 500-page document, and it was reviewing lots of different studies into the impact of various lifestyle choices on the probability of getting a whole range of different types of cancers. And the one study that I got picked up on by the media was one which was about the probability of getting colorectal cancer if you eat 50 grams of processed meat every day. So of this 500-page report with over 100 different studies in it, someone at the Sun newspaper had read this, or at least read part of it, and they had decided to highlight this study about processed meat and the chances of getting colorectal cancer if you eat 50 grams of processed meat a day. And they decided to sell this story under the admittedly inspired headline, "Careless Pork Costs Lives." And what they'd claimed in this eye-catching headline story was that eating a bacon sandwich every day increases the risk of colorectal cancer by 20%. Now, I saw this headline and I thought, that seems like a huge increase. Could it be that, say, if the background rate of getting colorectal cancer if you don't eat a bacon sandwich every day is 5%. Could it be that genuinely eating a bacon sandwich every day increases that risk by 20% to 25%? Do a quarter of all people who eat bacon sandwiches every day, or 50 grams of processed meat, as it was in the actual study, do they end up getting colorectal cancer? And so I decided that I was going to investigate the statistics, the truth behind this headline-grabbing figure. But before I had a chance to do that, the Sun had already launched the Save Our Bacon campaign, in which scientists were branded as health Nazis who declared a war on bacon, despite the fact that, of course, the original scientific article said nothing about bacon at all. It said about 50 grams of processed meat a day. But nevertheless, the Sun realised that pitching this story in terms of bacon, a butty, would strike at the heart of the British psyche, and it would sell papers. And indeed it did. It sold lots of papers on the back of the Save Our Bacon campaign. So where had this figure of 20% actually come from? Well, the Sun had calculated something called a relative risk. So they'd looked at a number of people in this study. So they'd said, of people that don't eat a bacon sandwich every day, 5 of those might be expected to get colorectal cancer during their lifetime. And then of the people that do eat a bacon sandwich every day, 6 of those might be expected to get colorectal cancer during their lifetime. And then what they've done is calculated this thing called the relative risk. Now, the relative risk is usually calculated for drugs or treatments which are designed to reduce the prevalence or the probability of getting a disease. So usually it's the relative risk is the risk with taking the disease, with taking the treatment, divided by the risk without taking the treatment. Now, in this case, the treatment is a relatively pleasant experience. It's eating a bacon sandwich. So they calculated the relative risk of getting colorectal cancer with eating a bacon sandwich, and they divided that by the risk without eating a bacon sandwich. They'd said 6 people get colorectal cancer when they eat a bacon sandwich every day and 5 without eating it. So they'd figured out that 6 divided by 5 is an increase of, well, an increase of 1 on 5 is an increase of 20%. So it gives you this value 1.2, and not this increase of 0.2 is an increase of 20% on the baseline risk of 1. So it is indeed a 20% increased relative risk. Of course, in the headlines, they didn't mention that this was an increased relative risk, but that's why it caught so many eyes. What would be more appropriate and more useful for us is not to know just what the increase in the risk is, but actually to know what the absolute risk is. So in the actual study, what they found was that of people in the survey who didn't eat 50 grams of processed meat a day, they found that 5 of those might expect to get colorectal cancer over the course of their lifetime. And when they studied people that did eat at least 50 grams of processed meat every day, what they found was that that number increased dramatically to 6 people in 100, or 6%. So really not a big increase in absolute terms, an increase of 1% for people that eat 50 grams of processed meat every day in their chances of getting colorectal cancer over their whole lifetime. So an absolute increased risk of 1%. But of course, the figure 1% doesn't sell many newspapers, whereas the relative risk of 20% looks much more dramatic. So you should be careful when you're just presented with one single headline figure. Usually if it's big and if it's a percentage, then you need to dig deeper to find out what the absolute risks are. There should be 2 figures, and they will usually be smaller, and they will give you a better picture of what the chances of getting the disease with and without that lifestyle intervention are. So I'd love to tell you that this was a problem that was just restricted to newspapers and the media, people who perhaps are less scientifically literate, but that's not the case. In fact, you see this sort of problem in scientific literature. So even scientists make these sorts of mistakes, and you also see it in patient advice literature. So this is a screen grab from a tool which was around, you can probably date it from looking at the screen grab. It was around in the early 2000s. It was called the Breast Cancer Risk Assessment Tool, and it was developed by the National Cancer Institute in the United States. And it was a tool which was designed to give people who were who'd been diagnosed with breast cancer the information about the risks of various different treatments that were available to them, both the chances of improving their conditions under that treatment, but also the potential side effects. And there was one particular drug that was on there, which is called tamoxifen, quite a famous drug, quite well known, which is used for treating breast cancer. And this is the way that this tool chose to present the benefits of taking tamoxifen. So it said women taking tamoxifen had 49% fewer diagnoses of breast cancer. That sounds brilliant. 49% fewer. That's a huge number of fewer cases. It's almost half the number of cases, which is fantastic. But when they presented the side effects of taking tamoxifen, they did it like this. The annual rate of uterine cancer was 23 per 10,000 for women taking tamoxifen compared to 9.1 per 10,000 in the placebo arm. That's really difficult to pass, I think. I think it's really difficult to read the way that they'd written it. And also, they'd used what we saw before called the absolute risks. So they used these 23 per 10,000. That sounds like a small figure, as does 9.1 per 10,000. So maybe this increased risk in getting uterine cancer when taking tamoxifen, maybe that's trivial. Maybe, this small number of cases really doesn't make a big difference. At least that's what you're meant to believe when reading this. And this is called mismatched framing. So when you present the relative risk of the benefit or the thing you want to emphasize and the absolute risks for the thing you want to downplay, so the side effects in this place, that's called mismatched framing, and it can really make a big difference to the way people perceive their risk. So what would be fairer than using this mismatched framing idea would be perhaps to present both of these things using the absolute risks, and that would be more informative. So for uterine cancer, we've seen that for people taking tamoxifen, there were 23 per 10,000 women in this trial that was done on tamoxifen. And for the women who weren't taking tamoxifen in the trial, the rate was 9.1 per 10,000. So an increase for people taking tamoxifen of 14 cases of uterine cancer per 10,000. And for breast cancer, for women in this trial, 34 per 10,000 when taking tamoxifen, which is a reduction of about half, as the relative risk suggested, from women who are not taking tamoxifen who got breast cancer with a rate of 68 per 10,000. So again, these are much fairer ways. And actually, you can see that the rates of getting breast cancer are not dramatically higher when given in absolute terms than the risk of getting uterine cancer. They are indeed a bit higher, but not orders of magnitude higher. Alternatively, if you're going to do this, and this is not the best way to present the risk, but if you are going to use the relative risk, then you need to present both the side effects and the benefits using the relative risk. So for breast cancer, we've already seen that tamoxifen gave 49% fewer diagnoses, which sounds like great news. But the reason why the uterine cancer figure, the increase in the rate of uterine cancer figure, wasn't presented using a relative risk is because it looks really, really bad. So this increase, you can calculate it from the absolute risk, this increase of 14 cases from 9.1 to 23 per 10,000, compared to a baseline of 9.1, 14 is an increase of 153%. So for uterine cancer, the relative risk looks like 153% more diagnoses, which is clearly not something that you want to be presenting if you're presenting this side effect and you're trying to sell this drug to people, which is not what the breast cancer risk assessment tool is trying to do. But even so, this bias, this mismatched framing may have been done subconsciously. And the irony is that if you just presented the absolute figures, you could see that taking tamoxifen reduces cases of breast cancer by 34, and it only increases cases of uterine cancer by 14. So overall, the net saving of 20 cases of cancer per 10,000 shows a significant benefit. So you don't need to try and, at least in this case, you don't need to try and fool people by presenting the risks in a different way. And actually, tamoxifen is a drug that's been used for a number of years for treating breast cancer because the benefits tend to outweigh the risks. So there are lots of different ways of trying to sell statistics if you've got a number that you want and you want to tell a particular story, then you can use statistics in different ways to highlight different aspects of that number. But sometimes there are some statistics that are so stubborn that you just can't bend them to your will. So what you can do, if you really want to tell a particular story, is what Donald Trump did back in 2015 during the runoff for the Republican candidate nomination for the presidency, and that is just to make it up. So this is an infographic that he retweeted back in November 2015. And I want to warn you that this part of the talk gets relatively serious. So this is an infographic which purports to show statistics about the ethnicity of people who were killed in the United States in 2015 and by whom they were killed. So by police or by white people or by black people. And so the statistics I want to highlight to you from this infographic that Donald Trump retweeted are these. So it suggested that of all the black people that were killed in 2015, 1% of them were killed by police. And of all the white people that were killed, 3% of them were killed by police. And the other two statistics I want to highlight are that of all the white people that were killed in 2015, apparently only 16% of them were killed by other white people. Whereas of all the white people killed in 2015, apparently as high as 81% of them were killed by black people. Now, I should preface this by saying that the source for these statistics is the Crime Statistics Bureau of San Francisco. And as a spoiler alert for what's coming up, I should tell you that the Crime Statistics Bureau of San Francisco is completely made up. It doesn't exist. And so that's a forerunner of what you're about to see. So I saw this infographic and I thought, I'm going to check these figures out because they don't sound quite right to me. So I went to the FBI website and I found out that actually the proportion of white people killed by other white people is not 16%, it's actually 81%. And of all the white people that were killed in 2015, the proportion that were killed by black people is not 81%, it's actually 16%. So these two figures, someone had gone to the trouble of actually looking up the correct figures and then just crudely transposed them to paint a very different picture about about who is killing whom in the United States. And the other two figures that I highlighted to you before in the previous infographic were that of all the black people killed in 2015, it said that 1% were killed by police. And actually, that figure is as high as 11%. And indeed, of all the white people killed by police, it suggested that was as low as 3%. And in fact, it's actually as high as 16%. Now, these last two statistics, these come from the Guardian website. And the reason for that is because back in 2015, the FBI were not keeping data about the ethnicity of people killed by police officers or law enforcement officers in the United States. And the director of the FBI, James Comey, said it's embarrassing that this British newspaper is keeping better statistics on this than we are. And he's absolutely right. So I had to go to the Guardian and look at their project, which is called The Counted, which was actually keeping track of these statistics to dig out those two figures. So these are the real statistics. Now, this was important because back in 2015, this was sort of the zenith of the first wave of the Black Lives Matter movement. It was an incredibly important movement in the United States, and it still is to this day. But it was reaching its zenith, and actually, by about a year later, the Black Lives Matter movement had made its way across the Atlantic to the United Kingdom, and it had started to raise the ire of some right-leaning journalists in the UK, in particular Rod Liddle, who wrote in The Sun in September 2016, he wrote the following on this very issue. He said, "There is no doubt whatsoever that the greatest danger to black people in the USA is other black people. Black on black murders average more than 4,000 each year. The number of black men killed by US cops, rightly or wrongly, is little more than 100 each year." And he finished with this. He said, "Go on, do the math." So obviously, reading this, I couldn't help myself but go and do the math. So firstly, a bit of fact checking on Rod Liddle's statistics. So Liddle said that black on black murders average more than 4,000 each year. By that, he meant that of 4,000 black people killed by other black people in that year. So I looked at 2015, which was the last year that Liddle could conceivably have gathered statistics for, should he have wanted to. And actually, in total, the number of killings in which the victim was black were only 2,664, so nowhere near this 4,000 figure that Liddell was quoting. And in fact, of those, 2,380 were committed by black citizens and 229 by white citizens. So nowhere near the 4,000 figure. Liddell also said the number of black men killed by US cops, rightly or wrongly, is little more than 100 each year. Well, again, looking at the Guardian's Counted project, you find out that the real figure is actually 3 times that amount. It's over 300 black people killed by US cops in 2015, so 3 times that amount. So firstly, his 2 statistics were exaggerated, one to make the number of black citizens killed by other black people much higher, and to make the number of black citizens killed by law enforcement officers look much lower. For balance, here is the number of killings in which the victim was white. So in total, 3,167, 500 of which committed by black people, 2,575 by white people, and 584 by law enforcement officers. So of these statistics, and one thing that Liddell really didn't draw anyone's attention to, and which I think it's important to draw attention to, is that of the total number of black and white people that were killed in the United States, about 45% of them were black and about 55% of them were white, which is pretty crazy when you consider that black people account for maybe only about 12% of the population of the United States. So black people are being killed with a disproportionately high rate in the United States. But that is not the story that Rod Liddell wanted to tell, but that's part of the story that I want to tell you this evening. So what about Liddell's other claim, his last claim? He said there is also no doubt whatsoever that the greatest danger to black people in the USA is other black people. So he's using those 2 figures in the previous slide, the fact that more black people are killed by other black people than are killed by law enforcement officers, to make this argument that the greatest danger to black people is other black people, not police officers. So to unpick that and to show you why that's a false argument, I want to do a little thought experiment with you. So in 2015, toddlers shot and killed 21 US citizens. It's crazy, but somehow these toddlers were left alone with guns and they managed to end up killing 21 US citizens. In the same year, bears killed just 2 US citizens. Okay, so toddlers killing far more people than bears. And then I'm going to ask you the question, who would you rather be left alone in a room with? Would it be a toddler or a bear? And I think the answer is quite clear for everyone. Of course, you'd rather be left alone in a room with a toddler. Toddlers don't kill more people in the United States because they're inherently more murderous or more dangerous than bears. It's because there are shed loads more toddlers in the United States than there are bears, and people come into contact with toddlers far more often than they do bears. And for exactly the same reason, black people don't kill more other black people in the United States because they're inherently more murderous. It's just that there are a lot more black people in the United States than there are police officers. And so what you really need to do is to account for the total size of those populations, the population of black citizens in the United States and the population of law enforcement officers in the United States. And then you need to divide the number of killings by the size of the population to calculate what's called the per capita rate of killing. And that helps to answer the question, if I'm a black person walking down a dark alley and someone is approaching me and I'm worried that they might kill me, who should I be more concerned about it being? Should I be more worried that it's another black person, or should I be more worried that it's a police officer? So let's figure that out. So in terms of the mathematics, the number of, we've seen these statistics already, of all the people in 2015 who were killed who were black, 2,380 were killed by other black citizens and 307 by law enforcement officers. Now, when you take into account the sizes of these 2 populations, there are over 40 million black people in the United States, and there are just 635,000 law enforcement officers. And so to calculate the per capita killing rate, you need to divide this number of killings by the size of the population doing the killing. Okay, so it turns out that for black people, the rate is just about 1 in 17,000, whereas for law enforcement officers, it's way, way higher. It's 1 in 2,000 almost. So much, much higher than the rate of killing by black people on other black people. So way, way higher for law enforcement officers, which really tells a very different story to the story that Rod Liddell was trying to tell us. Now, there are some caveats to this in that, of course, law enforcement officers are routinely armed. They're also often in the course of their work going in to conflict situations where perhaps in the United States gunshots are more likely to be fired. So there are caveats for why this rate might be higher, but nevertheless, the per capita rate of killing for each member of this population is way higher for law enforcement officers than it is for other black people. So it gives the lie to this idea that black people should be more scared of other black people than they are of law enforcement officers in the United States, and it really changes the point of view that Rod Liddle was trying to put across. So the take-home messages from this part of the talk. Firstly, when it comes to medicine, when it comes to reading newspapers, when it comes to listening to the radio and the TV, you need to look out for these relative risks. If you're just given a single figure, usually a percentage, and often if it's large, then you need to be aware that that might be a relative risk. If you really want to know a comparison between two different treatments or two different lifestyle choices, then you need to know what the risk is with doing that treatment and without, or what the risk with doing that lifestyle choices and without doing that lifestyle choice, if you want to make a fair comparison and understand the magnitude of the size of that risk. The other thing, of course, is that you should be aware of mismatched framing. So if you see one statistic painted as a relative risk and the others downplayed as an absolute risk, then you should of course be wary of what this story is trying to tell you, what this newspaper story, or what you're trying to be sold by this company who's telling the story in this particular way. So be aware of this mismatched way that things can be framed. And the final piece of advice from this, which is probably good advice for everyone in every country, is don't trust politicians, because they lie out of their teeth all the time as part of their job. Okay, so less of a mathematical message, more of a philosophical message there. Okay, so in that last segment, I'd actually already segued into the mathematics of crime, looking at those killing statistics from the United States. And I'm going to continue on that theme, but I'm going to take a little mathematical diversion to build up some maths that I'm going to need to look at a particular problem that I'll present later in this section. So I'm going to start by introducing a relatively famous mathematical problem called the birthday problem. And if I was doing this talk in the room with you, then I would be saying, what's the probability that two people in this room share a birthday? Unfortunately, we're doing this virtually, so I'll rephrase that question. And I'll say, perhaps put it another way, how many people do I need to have in a room before the probability of two people having the same birthday becomes more than a half, before it becomes more likely than not that two people share a birthday? Now, I think when most people think about this problem without thinking too hard about it mathematically, the number that comes to mind is probably 180 or so, because that's about half of 365, the number of days in the year. So perhaps 180 people will be enough to make sure the probability of two people having the same birthday becomes more than a half, becomes more likely than not. And actually the real answer, and the reason why this is a famous mathematical problem, is because the real answer is really surprising. In fact, you only need 23 people in the room for the probability that two of them sharing a birthday becomes more likely than not. Now, that seems like a surprisingly low number. So where does that 23 number come from? Well, I'll try and introduce it to you in the following way. So really what's important when we're thinking about this birthday problem is not how many people there are in the room, but actually how many pairs of people there are in the room. Because we're talking about two people sharing a birthday, and that's something that pairs of people do together. So I want to work out a formula for how many pairs of people there are in the room when I've got a certain number of people in there. And I'm going to start by doing it with just 5 people, because I know that I can check that relatively easily. So I've got 5 people here, my maths reservoir dogs. I've got Mr. Green, Mr. Orange, Mr. Purple, Mr. Blue, and Mr. White. And I'm going to figure out how many pairs there are. And to do that, I'm going to get them to shake hands with each other. And you can tell that I developed this idea before the times of COVID, because actually now they should be fist bumping, or they should be, elbow bumping, or they should probably be standing across the room and nodding at each other, or maybe even just outside somewhere that's well ventilated and socially distanced. Anyway, let's pretend that they can shake hands with each other. So here's Mr. Green. He shakes hands with Mr. Orange and Mr. Purple and Mr. Blue and Mr. White. And that's 4 handshakes for the 4 other people in the room. And then Mr. Orange steps up and he can shake hands with Mr. Purple and Mr. Blue and Mr. White. And that's 3 more handshakes added to the total. And then Mr. Purple steps up to the mark and he can shake hands with Mr. Blue and Mr. White, and that's 2 more handshakes. And the last handshake that hasn't happened yet is between Mr. Blue and Mr. White, and that's 1 more handshake. So it's no coincidence that with 5 people in the room, I start at 4 and I add up 3 and 2 and 1. I add up the consecutive whole numbers going up to 1 below the number of people in the room, so 4 in this case. And when I add those up, it's quite simple. It's just 10 people in the room. So I know there are 10 handshakes or 10 pairs of people when I've got 5 people in the room, but I want to generalize this to make it more general. So what happens when I've got more than 5 people in the room? Well, I'm going to take another diversion in order to be able to answer this. So these numbers, when you add up the consecutive whole numbers, they're called triangular numbers. Why are they called triangular numbers? Well, let's see. Hopefully, if you were brought up in Britain, then you will know the song The 12 Days of Christmas. If you weren't brought up in Britain, then it's a crazy song. It's about a boyfriend or girlfriend that you've got, a partner, your true love. They send you presents out after Christmas. For each of the 12 days after Christmas, they send you presents. On the first day, they send you a partridge in a pear tree. On the second day, let's assume that partridge in a pear tree is just one present for the sake of argument. They send you the partridge in the pear tree on the first day. On the second day, they send you the partridge in the pear tree and the 2 turtle doves. So that's 3 presents on the second day. On the third day, they send you the partridge in the pear tree and 2 more turtle doves and 3 French hens. And then on the 4th day, they send you the partridge in the pear tree and the 2 turtle doves and the 3 French hens and 4 calling birds. And then on the 5th day, they send you all those presents again, plus 5 gold rings. That's how you sing it in the song. That's when you get to 5. So that's 5. And that's the reason why they're called triangular numbers, because you can array them, you can arrange them in this nice triangular shaped array. And people who are interested in snooker will be familiar with this, because when you make the triangle of reds, you make a nice triangular shape with it, and that's 1 red ball at the top, 2 in the next row, 3 in the next, 4, and then 5. Okay, so it's the same number as this. So the question I'm going to ask is, how many presents did my true love send to me on the 5th day of Christmas according to the song? So how am I going to calculate this? Well, let's start by rearranging these objects. So let's start by making them into a different sort of triangle, a right angle triangle. And then I'm going to bring on a whole second set of these objects to make another different shape, in this case a rectangle. So now I've got a rectangle of objects, which is going to be easy to calculate. So I just need to calculate or multiply the number of rows, 5, by the number of columns, 6. Okay, so I've got 5 rows because that was the number, that was the 5th day of Christmas. And I've got 6 rows, 6 columns, because there's 1 extra when I've added this on. So generally I'm going to be calculating n, where n is the nth day of Christmas. I'm going to be calculating n for the rows times n plus 1 for the columns. So that's going to give me the number of objects in this rectangle, but I've got to remember to divide by 2 because I've added in twice as many of these objects as I should actually have. Okay, so the formula for the number of objects that I would get on the nth day of Christmas is n times n plus 1 divided by 2. Okay, so when I plug that in for 5, that's 5 times 6 divided by 2, which is 15 presents, which people who play or watch snooker will be familiar with, the fact that there are 15 red balls in this array. So that's good. That's my formula for the number of presents on a particular day of Christmas, and it generalizes. How does that work out for handshakes? Well, with 23 pairs of people in the room, the first person can get up and shake hands with 22 other people. The next person with 21, the next person with 20, the next person with 19. And I don't know why I animated the whole of this triangle, because of course I've now got a formula to work this out. Anyway, I need to work out the sum of all the consecutive integers from 1 all the way up to 22. And I've got this formula for that. It's going to be 22 times 23, so n times n plus 1 divided by 2. And that's going to be 253. So when I've got 23 pairs of people, I've got 23 people in the room, I've actually got 253 pairs of people, which goes some way to explaining why it's so much more likely to have pair of people that share the same birthday in the room than you would expect with just 23 people in the room. But I'm not done yet. So I figured out that with 23 people in the room, there are 253 pairs of people, but I actually want to do the calculation that tells me what the probability of 2 people sharing a birthday is. So how do I get get to that? Well, firstly, I'm going to work out what the probability, little p, of one pair of people not sharing a birthday is. So the way to work this out is a bit like we did with the mammograms earlier, and working out the probability of false positives. It was easier to work out the probability of not having a false positive first, and then working out what the probability of getting a false positive, or at least one false positive, was by subtracting that value from 1. So I'm going to do exactly the same thing here, and I'm going to start with just one pair of people. What's the probability that one pair of people don't share a birthday? Well, the first person can have their birthday on any day of the year. I've put this one here, that's my birthday, April the 4th. And the other person in the pair can have their birthday on this day, or on this day, or on this day. Don't worry, I haven't animated them all. On this day, or on this day, or on this day. And so, in fact, that person can have their birthday on any of the remaining 364 days of the year. So the probability that when there are just two people in the room, just one pair of people, the probability that they don't share a birthday is incredibly likely. So the probability they do share a birthday is really unlikely. It's 1 divided by 365. So that's where we're starting off. Now, what happens if I take that probability and I try to figure out what the probability, capital P, that 253 pairs of people don't share a birthday? Okay, so I have to think, well, if I need one pair of people not to share a birthday, but I also need the next pair not to share a birthday, and the next pair, and the next pair. And if those birthdays are all independent, then I need all 253 pairs of people not to share a birthday, which means I have to multiply that probability of one pair of people not sharing a birthday, 364 over 365, by itself 252 more times, or equivalently, I raise it to the power of 253. Now, this number, 364 divided by 365, is pretty close to 1. But actually, even when you multiply a number, even a number that's that close to 1, by itself enough times, then that number starts to get smaller and smaller. The product starts to get smaller and smaller. And so actually, by the time you've done it 252 times, the probability that two people in a room of 23 don't share a birthday is 0.4995, so just below a half. And so that means the probability that two people, or at least two people, do share a birthday in a room with 23 people in is just above a half. It's 1 minus that figure. Okay, so for different numbers of people in the room, I've plotted the way that the probability changes with the number of people. So I've got number of people on the horizontal, or the x-axis at the bottom there, and on the side, on the y-axis and the vertical axis, I've got the probability of seeing a match. And so what you can see is as the number of people in the room increases, the probability of having a match increases. And I stopped it here at 23 people to show that the probability of having a match becomes bigger than a half when you have 23 people in the room. And you can see by the time that I've got up to maybe 60 or 70 people in the room, the probability of two people sharing a birthday is almost certain. And so when I'm doing this talk with people in person, I often get people to try and make a bet with me. So I will often put £1 on and say, I bet two people in this room share a birthday, even when there are small numbers of people in the room, as long as there are more than 23. And see if someone will take the corresponding other side of that bet. And people always do, because they think it's so unlikely that two people will share a birthday. And in fact, even if there are people not willing to take me at 1-to-1 odds, as long as I've got enough people, maybe I've got 60 people in the room, I can offer odds of 10-to-1 and still expect to make money on that bet. So it's a surprising result, and I think it's something that people really find difficult to intuit. So I've done some theory with you, you've done a little bit of mathematics, but what about the actual real world application of this? Does it actually work in reality? Well, back in 2014, the World Cup was hosted in Brazil. And the great thing about the World Cup in 2014 was, apart from various of the games, the really great thing for a mathematician was that each of the squads had 23 players in it, this magical number where we would expect the probability of two people to share a birthday in that group of 23 to be more than likely. So more likely than not, but only just. Okay, so it's about a half. So this is the Brazil squad of 23 people, and lo and behold, you've got Hulk and Paulinho who share a birthday on the 25th of July. So it works in this case, but that's just one example that I could have cherry picked. There were 32 teams in the World Cup in Brazil in 2014. And the great thing is that if you're a mathematician and you are so inclined, then you can look up the birthdays of all the 32 times 23 people who played in that World Cup or who were part of squads in that World Cup, and you can figure out, of all those 32 teams, what proportion of them had two players, or at least two players, that shared a birthday. And if you chose to do that, as a mathematician might have done, then you find that exactly half of the squad, so 16 out of 32, have two players, or at least two players, that share a birthday. Now, that's what this probability would have predicted. That would be your best estimate of the number of teams. Of course, it doesn't always work out to be perfect, that it's going to be exactly a half of these teams. It is probability, it's random, so you'd get more or less on some occasions. But the fact it works out at 16 out of 32 is so beautiful, and it really demonstrates that this formula does indeed work in reality. So I'm just moving on to the last part of the talk now, and I want to warn you that this part of the talk is a little bit more serious and potentially upsetting, but I think it's important to talk about it. So back in May 2017, a few days after, this was the scene in St Anne's Square in my hometown of Manchester. And the reason all these floral tributes and balloons were laid out in St Anne's Square was because on the 22nd of May 2017, about 10 o'clock, 10:30 in the evening, an Ariana Grande concert was spilling out, and young people who'd been at the concert were in the foyer meeting up with their parents, and people had come to pick them up and heading home. And at the same time, Salman Abedi walked in alone wearing a rucksack full of explosives and bolts and nails and screws, and he blew himself up, and he killed 22 innocent people that evening in Manchester, people who were young and in the prime of their life, and he took that away from them. And as I mentioned, my hometown was Manchester, and I'd been to concerts at this arena. It was called the MEN Arena at the time, Manchester Evening News Arena. And at the time, I was particularly interested in following this because it struck home. This was in my hometown. This felt like it could have been me. But at the time, I wasn't in Manchester. I wasn't even in the UK. I was in Mexico. And because of the time delay in Mexico, we were in the middle of the afternoon when this was happening. And I followed this avidly throughout the rest of that day as the news stories came in. And actually, probably the most of the rest of the people in the United Kingdom were still asleep, only to wake up to this horrible story the next day. I followed it with great attention over the next few days precisely because it was in my hometown of Manchester, and it really struck home to me. But what I noticed over the next few days was something interesting about the date, the 22nd of May. I noticed that exactly 4 years before, in another Islamist terrorist attack, Fusilier Lee Rigby was brutally murdered outside his barracks in Woolwich. And I thought that is a strange coincidence for these two Islamist terrorist attacks to have occurred within 4 years of each other. And I wasn't the only person to have noticed this coincidence. So the Daily Star ran a headline which said, "Dates matter to jihadi terrorists. Manchester Arena attack on Lee Rigby anniversary." And in that story, it was basically based on a tweet by Sebastian Gorka, who was then President Trump's deputy assistant. And he said, "Manchester explosion happens on 4th anniversary of the public murder of Fusilier Lee Rigby." And he concluded from that, "Dates matter to jihadi terrorists." And I read that tweet and I thought, is it true? Is it true that jihadi terrorists are really organised and can strike at will, meaning that potentially we should be more scared of them? Or is it really the case that actually they don't really know what they're doing and they're just opportunists that take any opportunity that comes along, and they don't really have this great organisational power so that they can strike at will? And so I wanted to figure out, if terrorist incidents were just happening purely at random, what's the probability that two of them would occur on the same day? Unfortunately, we have just that information from the birthday problem. So are terrorists really that coordinated that they can strike at will? Well, I went up and looked up all the terrorist incidents that had occurred against Western nations, Islamist terrorist incidents, I should say, against Western nations between April 2013 and April 2018. And it turned out that there were 39 of these terrorist attacks. And I went back to that graph that I showed you earlier, and I plotted this on, and I said, well, with 39 terrorist incidents, even if they were all occurring completely at random independent days of the year, random days of the year, the probability that two of them would occur on the same day of the year purely by chance is nearly 90%. In short, we should be far more surprised if two of them hadn't occurred on the same day of the year than when two of them eventually did end up occurring on the same day of the year. So it puts the lie to this idea from Sebastian Gorka that somehow just because these two terrorist incidents occurred on the same day of the year, that somehow means that these terrorists are organised. You know, he was tweeting during this conclusion, trying to further his anti-Islam agenda in the United States, making us more scared of these terrorists than we should really be, doing the terrorist job for them, in short. So I want to finish with these take-home messages. So firstly, this last story illustrates that coincidences, although they seem unlikely, they are surprisingly likely to occur given enough time and enough chances and enough events. Coincidences can be surprisingly likely, but as humans, we're great at spotting these patterns. And then our next thing to do is to draw a causal inference based on spotting that coincidence. And actually, that's not always the best thing for us to do, because coincidences do just happen. You might walk down the street and see someone you haven't seen for 10 years, but it doesn't mean that somehow magically there's some meaning behind that. Usually, at least there isn't. So coincidences can be surprisingly likely. Another message that I want to come across, not just from this part of the talk, but from the whole talk, is that we shouldn't be blinded by the illusion of certainty. The idea that people that wield the numbers are always in possession of the whole truth. So, you know, it might be you that's convicted incorrectly by a doctor who is a medical expert, but not an expert in statistics, yet they came up with statistics which gets you convicted. This is a sort of story which comes up all the time in the Maths of Life and Death in my book. You know, you might be given the wrong information by your doctor because despite the fact they're a fantastic practitioner, maybe they're not on top of the statistics. You might read something in the newspaper and change your lifestyle because of that thing you read, because of the increased risk you read about, but actually that risk was a relative risk and not an absolute risk, and actually the real danger was massively over amplified. So when you see statistics out there in the wild, remember that statistics can be manipulated to tell a particular story. Numbers are not always these nuggets of hard, objective, unquestionable truth that we like to think they are. And so we need to question numbers and question the people who might wield those numbers against us. And the last message from the talk, as I mentioned, I often use this talk to make a bet with people, to try and fleece money out of innocent attendees of this talk. So I would say, if a mathematician offers you a bet, don't take it. So beware of mathematicians bearing gifts. So that's where I'll finish. And I'll say thank you to you for listening. This has been an absolute pleasure to give this Gresham lecture, and I hope to see you again soon.